And in this chapter, let's say all of the V's are in a product space. Or IPS. And all of the E's are subspaces of V. Right, definition. So if a vector belongs to the inner product space, then we say the orthogonal projection is
Was that a V or a U?
V.
Okay.
Of the vector V onto a subspace E is a vector W that belongs to V with two properties. The first one is W belongs to E. The second one is V minus W is orthogonal to the subspace.
As in like the vector addition of negative W?
Yes.
Okay.
And we write W is the projection of V onto E. Okay. So we can draw example. In R3, our plane can be a subspace. And then we have a vector V in R3. So what we're doing is we want to find a projection on E. And this is our W. And this V subtract W is this vector right here. So this is orthogonal to the plane.
I see. Yep. Is it provided that V is not like for instance, what if V is along the axis? Like one of the axes. So E is straight up. I mean V.
Oh, then then we would end up with we like just a point or the zero vector on the plane. Like if it's this case, then the projection would be just the zero vector.
Oh, okay. There is no W. Or W is the zero vector?
Yeah, W is the zero vector.
Oh, okay.
Okay, Proposition. So if E1 through VR are orthogonal bases for E, and we have a vector V belongs to the inner product space V, then W would equal to alpha 1 V1 plus dot 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 plus alpha R VR, where alpha i's equals the inner products of V comma VI. Divided by the norm of VI squared.
So
And
like the definition of the orthogonal basis. I mean, the definition of AI, alpha I for the orthogonal basis.
yes. And so if we define it like this, then it will satisfy OP1 and OP2. And in this case, such W is the projection of V onto E. This is so basically this proposition is saying that the projection of V on E equals the sum of V comma VI over the norm square multiplied by VI. I from 1 to R.
Mhm.
Okay. So so we can check OP1. So OP1 says that all of the we should have all of the W's in E. So if W can be written as a linear combination of the bases, then by closure, we know that.
So is the I guess if it's a basis for E, it's also a if something is a basis for a subspace, it doesn't necessarily mean it's a basis for the vector space, right?
It's not, but it
it's
can be
not
like a part of the
a
basis.
part of the basis. Okay, yeah.
Yeah. So by closure of the basis vectors, okay. And then for OP2, we need to show that V minus W is orthogonal to E. So since E is composited with like R V1 through VR, so those are bases for E. So then we can change this statement to showing like V minus W is orthogonal to all of the VI's. One, two, R. because VI is a spanning set, and we had a proposition on, not proposition, yes, a proposition saying if W spans, then V is orthogonal to W means V is orthogonal to every V. So then we can write, so this orthogonal, we need to do a inner product and to show that is 0. So let's do a inner product of V minus W comma VI. Okay, so we can represent W as alpha 1 V1 minus all the way to alpha R VR VI. And by linearity, we can take all of these ones out. So we will have a V comma VI and subtract alpha 1 V1 VI. Same thing, subtract alpha R VR VI. Okay. Now, so let's take one of the term out. So wait, no, so since all of the VIs are orthogonal bases, therefore we can so the inner product of VI Vj would be 0. But what we are left is somewhere here there is a AI VI VI.
Oh yeah.
Right. So this equation is left with the first term V comma VI and this middle term minus alpha I VI VI. Okay.
I thought I thought you can only take alpha 1 I mean V1 VI to alpha R VR VI as 0 if it's like 0, like if it equals the 0 vector. Like this linear independent thing.
Say it again.
I guess can you explain the alpha I VI and V1 VI equals 0? Alpha 1 VI V1 VI.
Oh, because these two V1 and VI, they are from the orthogonal basis. So if these two are orthogonal, means that the inner product of VI Vj is 0 if VI does not equal to Vj. Like I just
the pairwise orthogonal thing, right?
Yes.
Oh, okay.
Okay, so then since like all of these are orthogonal, these are just 0, and subtract 0, we just not writing them. And and what we have here is a alpha multiplied by a inner product, and we know what alpha can be equal to. So let's substitute that. Subtract alpha I is v comma vi over the norm of vi squared. Okay, multiplied by vi. All right. So then this inner product of vi, we know that's equal to the norm of vi.
Yeah.
So then we can again rewrite this equation to v comma vi subtract v comma vi over the norm of vi. All right, and now these two can divide out. And what we have left is just the inner product of vi subtract the inner product of vi, and these two are the same, so 0.
Mm.
And now we've proved that v minus w, take the inner product with vi, would be 0. So that means these two are orthogonal to each other.
Yeah.
Right. So v subtract w is orthogonal to every vi, means v subtract w is orthogonal to the subspace E. And we're done with our proof.
Cool.
Okay. So so for this projection, what we are doing is actually to find a closest point. So if we have a point on the space is at the tip of the vector, and then we want to find on the subspace E where is the closest point to this point. So from geometry, we know that we find a orthogonal or perpendicular line and find the point that's intersect with the subspace. So here is the point that's closest to the given point. So let's prove that the projection is linear. So I have a proposition. Suppose we have V1 through VR. Is an orthogonal basis for E. Then the map. So the projection is we take a vector V, and V is inside of this inner product space. And we project it onto E. E is a subspace of V. So E, like whatever is in E is also in V. So we can write this map as a input from V, and we take it and the output is also in V. And we say this is linear, we claim that.
So when you say a map is linear,
Mm.
I mean like a map is just a function, right? So
Yeah, or the transformation.
oh, okay.
So for linearity, we basically prove that alpha beta thing. So
Mhm.
projection onto E of alpha V plus beta W, where V and W are in V. Okay.
Mhm.
So we can use the definition from the proposition on the top. Basically, that will equal to the sum of I from 1 to R. And on the top, we have the inner product of alpha V plus beta W, comma Vi over the norm square of Vi multiplied by V.
Mhm.
And now, by linearity, we can by linearity of the in the product, we can take the alpha V and beta V out.
Mm.
So it'll be alpha V Vi over Vi from 1 to R plus beta W Vi. Okay.
Mhm. Oh,
And
and the VI still. Oh no, you multiplied it in.
um
Isn't there still a VI on the side?
yeah, we can take the factors outside. Okay, and that would be equal to, so again by linearity, take the alpha outside. You're left with the sum of V comma Vi over Vi square. Oh, I forgot this Vi. That's what it said.
Yeah. Oh, okay.
And then beta equals 1 to R W Vi over V. All right. And then again, by definition, these two are just the projection of V onto E. So this will be a PEV plus beta PEW. And that's the end proof of linearity.
Yeah.
All right, so new theorem. So let E to be a subspace of an inner product space V. I think that's written here. Good. So then if we have a vector belongs to the inner product space V and W also belongs to V, satisfying OP1 and OP2. So the first theorem is saying for all x belongs to E, V minus W, the norm of V minus W is smaller than or equal to V minus X. So that's the, this is the V minus W. We say, basically, if we have another vector, like any other vector on E, for example, here, then V minus X, like this one, it will have a greater length than V minus W.
Oh.
And the second one is for some W, if for some X, if we found a X, if we found some X that V minus W equals V minus X, then W has to be equal to, X has to be equal to W.
If
This is the uniqueness of W. If we know that X is belong to E, and we let a Y vector equals to W minus X. Okay. And we have V minus X equals, so for this one, we are just doing like vectors. So if we are taking one vector multiplied by another, it will be the same thing as if we subtract a third vector and then add a third vector minus X. Because these two will just be 0. So this technique is actually always used in proof. We subtract something and add something. Okay. And then we already define y equals w times w subtract x. So this becomes v subtract w plus y. All right. Now we know that v subtract w is orthogonal to the subspace E by OP2. And we know W and X all belongs to E. Because W is the projection and E, we defined it in E. X, we defined it in E. So now, if V minus W is orthogonal to E, that means V minus W is orthogonal to any vector E. So then, V minus W would be orthogonal to, if it's orthogonal to both W and X, then it will also be orthogonal to W minus X. Because W minus X will also be in E. And we call this Y. All right. Now, by Pythagorean identity, you know that E minus X norm square equal to Let me turn on the air conditioning. So we know that v minus x is the same as v minus w plus y. So let's substitute that to v minus w plus y squared. Okay. And that by Pythagorean identity is equal to, we take the norm of v minus w squared plus the y squared. And then we have, so this y squared, we know like it is non-negative. It's greater than or equal to 0. Therefore, we have a number equals another number plus a non-negative number. So v minus x norm square has to be greater than or equal to v minus w norm square. Then in the end, we just take the square root on both sides. Okay, the second one is we want to prove if these two are equal, then x has to be equal to y. Right, so now let's go from here. Then if v minus x equals v minus w, it means y is 0. So if v minus w equals v minus x, therefore the norm of y squared equals to 0. And by the fourth property of the norm, we know that it's non-degeneracy. So the norm of y equals 0 means that y is a 0 vector. And if y is a 0 vector, we define y to be w minus x. So w vector has to be equal to x. And whenever we want to find a projection, we can always find a set of orthogonal bases. And then from here, we use the definition of that alpha equals something and to find the orthogonal projection. Then we can move on to our last section, 5.4, least squares. So whenever we're given a set of data points, for example, we have 4 rows of data points of x and y here. And we want to do a linear regression to find the line that match these data points so that we can predict future points. For line, we would have y equals alpha plus beta x. And we have our x and y. So that means I have alpha plus beta 1 equals 6. Alpha plus beta 2 equals 5. Alpha plus beta 3 equals 7. Alpha plus beta 4 equals 10. So we plug in the x and y. And then, given these four equations, we can write a matrix multiplication equation. So the alphas are all ones. So I have 4 ones. And then when we multiply by the vector, the unknown vector, the first one is alpha. And for beta, they are 1, 2, 3, 4. And this will equal to our y values 6, 5, 7, 10. However, we cannot solve this equation because it's overdetermined. We have way more equations than what we need. We have 4 equations for 2 unknowns. So what we can actually do is just to find the closest line that match all of the data points. And what does closest mean? So we sometimes use MAE, mean absolute value, or mean absolute error, or sometimes we use mean square error to determine what we need. So these two are 2 different metrics that we want to minimize. We either minimize the absolute value of a data point to the line, or we minimize the square distance from a data point to the line. So the square distance, basically like if a point is way further to the line, then we punish it more, comparing to like a bunch of other lines, a bunch of other points that's quite far but not as far. Matrix A multiplied by x equals b, although this x is the alpha and beta here. And now to find the x that's closest to being a solution. The norm of ax minus b. And find a x that minimizes the norm. So because like if we subtract b on both sides, then what we want is a ax minus b equals the zero vector. So then if we minimize that ax minus b, we would find a x that's that makes the expression closest to the zero vector.
Because when the norm equals 0, the length equals 0. So, oh, so it's like just on the point.
Yeah, this is like so we want a ax minus b solution. So what we actually want is ax subtract b equals 0. And then we want a solution that makes this expression closest to 0. And we know the length of 0 is just 0. So we want this to be closer to 0. And we know the norm is non-negative, so closer to 0 means minimize it. So then what we really want is to minimize ax minus b norm square. Okay, so consider we have a n by n matrix A. For each row, we do a ax subtract b, and in the end, we add them together after square them.
Okay.
Right, and this is what we call the least square. Now we want to actually find the x. So how to find the x? Let's consider all x in the vector space. So after the mapping, they will all be mapped to our output vector space. And then it means that we are looking for this equation, like the result of the equation in the image of x. And then we find the x that makes the distance smallest. So we are actually looking at the range of A, or the image of A. Therefore, minimizing the square, the norm of ax minus b, is the same thing as minimizing the distance between b to the image of A. And to find the closest point, we know our orthogonal projection is a way to find the closest point of the subspace to a given vector. And we know that the range of A is actually one of the subspace for Rn. So what we want in the range of A is the projection of V on the range of A. So orthogonal projection. And we know it belongs to the range of A. We have a idea of what we want to do, and we know how to do the projection. So what we need to find is a set of orthogonal bases in the subspace, and then we can use this formula to actually find the orthogonal projection. Now what we need to do is to first find a set of orthogonal bases of the subspace image of A. Okay, and then we use formula to compute the projection of B.
The formula is just the sigma I to R
Yes.
B whatever. Okay.
And then we just do some row reduction to find the X. Recall if we have a W equals the P projection of W onto a subspace capital W, projection of V onto W, then that means my v minus w equals 0 vector. I mean, it's orthogonal to the subspace W, and that's by OP2. So then, if my equation AX equals the B project onto range of A, then it means B minus AX is orthogonal to the range of A.
V minus W.
Yeah, so this vector minus this one.
Yeah.
Okay. And now, so if A is a linear transformation and so when we have a transformation, then we know that from from here we know the basis of the range of A is these two columns. So that means these two columns are spanning and linearly independent, but all of the columns, like if we consider all 5 columns, these 5 columns spans A. I mean, span the range of A. Because 2 columns would make a basis. So adding more columns, like adding more vectors, would span, but the only thing is that they're not linearly independent. Okay, so then back to our page. So the columns of A let's say we call them A1 through AN because we have n columns. So they span the range of A. Okay, now we say, now by the other proposition in the orthogonality, we know that B minus AX is orthogonal to A, to the range of A, means that B minus AX is orthogonal to all column vectors in A.
Yeah.
For all AI, for all I belongs to 1 to n. Okay, and now the orthogonality means that we can write it as an inner product equal to 0. B minus AX comma AI equals 0. Okay. Okay, now we know how to compute the inner product. That's basically the AI dagger multiplied by B max AX. And then we can further simplify this. So AI dagger is the like the each columns. So that's like the conjugate transpose of each column. Okay, and then if you're talking about every AI, we can basically compose them to the A, but also do a conjugate transpose multiplied by B minus AI, and I want this equal to the zero vector.
Mm-hmm.
This is for all.
Yes.
Alright, and then I have let's simplify this. We have a multiplied by in the parenthesis, so we can do a distribution. So we will have a dagger B subtract a dagger A X equal to 0. Alright, and then we add this on both sides. So we will have a dagger B equals a dagger AX. Okay.
Mm-hmm.
Now let's do an example. Okay. So let's find the example we talked about.
Mm-hmm.
Let's do find alpha beta. Okay, so we have the equation 1 1 1 1 1 2 3 4 multiplied by alpha beta equals 6 5 7 10. Right. Now we set the equation. We know that a dagger in this case would be since we all have the real numbers, so we can just do transpose. So on the left hand side would equal to 1 1 1 1 1 2 3 4 multiplied by the b vector 6 5 7 10. Okay, and on the right side we have the a dagger again multiplied by a, so 1 1 1 1 1 2 3 4. Say
Mhm.
multiplied by x alpha beta. So at the end, I've got alpha equals 7/2, beta equals 7/5. And these two are our alpha plus beta y equation. So let's plot them in decimals and check the graph. Okay, now we have 4 data points, and we have the line that based on least square that maps that actually matches the trend of our data points. So then we can make prediction like what does y equal when x equals 6 and stuff.